So good afternoon, everyone. Welcome back to Math 122. We're going to keep on going in the same direction today, finishing up sections 2.5, and I think we're going to finish 3.1 as well, because 2.5 is pretty light. So we're going to start Chapter 3. The notes for Chapter 3 are posted onto the Blackboard. If you have an iPad or whatever, you can download them onto there from Blackboard. And I'm going to be updating the notes for Chapter 2 after today's class and after I upload the video. So regarding your homework, you have homework assignments, which are due on March 1st, so that's tomorrow, and then on March 3rd, that's Friday, I think. So those are the two homework assignments that you have right now. I posted also a homework assignment for 3.1 and 3.2, which we're going to finish this week. The homework assignments are going to be due on the Monday after spring break. So that's like March, I want to say it's March 13th. So that's when those homework assignments will be due. Your next quiz is going to be this Thursday in class. It covers sections 2.2, 2.3, and 2.4. Office hours. I just want to remind everyone that on Tuesdays, I'm in the Math Tutoring Center. Okay, so I'm not in my office on Tuesdays. I'm in on the first floor of LeConte in LeConte 102. And then on Wednesdays and Thursdays, Wednesday 3 to 4, Thursday 11:30 to 1, then I'll be in my actual office in 439. Okay, so Tuesdays I'm in the Math Tutoring Center. And if it's not a Tuesday, then the Math Tutoring Center will still have people in it from 10 a.m. to 4 p.m. You can go get help from another math grad student. Or you can go to the SI sessions and get help. Any administrative questions before we start in on content for today? Okay. Well, let me just comment on the exam. I was quite pleased with the results. Actually, the average for the exam was the highest average I've ever had on an exam, so good job. Give yourselves a round of applause. Fantastic job. No, seriously, the average for the exam was like an 89% or something like that, so quite high. So good job. I was really pleased with all of your work, and I appreciated all of your comments on the last page on the bonus. I always like to read through those as I go through the exams. Helps me stay sane while I'm like sitting down grading for 6 hours straight. So that's the exam. So let's, without any further ado, get back into what we were talking about last time. So last time we talked about a little bit more about tangent line approximation, which I'm not going to go over that again now, but I'm going to let you know that you need to know how to you need to memorize this formula for tangent lines, and you need to know how to use it to do tangent line approximation, okay? So this is never going to go away. We're going to be doing tangent lines for like the rest of the semester. This isn't one of those things that you can kind of just sneak by without memorizing this or learning how to do tangent lines, okay? So we're going to talk more about tangent lines later on. But the bulk of the lesson last time was about concavity, okay? So concavity and the second derivative, okay? So what I want to say about the second derivative is that, look, derivatives in general tell us about how the parent function is behaving. And the second derivative, okay, can be thought of as the derivative of the derivative, okay? So it's going to tell us how the derivative is changing, okay? The second derivative tells us how the derivative is changing, okay? So if the first derivative tells us the slope, then the second derivative tells us how the slope is changing, okay? Whether the slope is increasing, okay? If it's increasing, it looks maybe something like this, right? Slope is increasing, then we're concave up. Right? It tells us something about the curvature, okay? So there's sort of three levels. There's the function itself, which tells us height, okay? And then there's the derivative, which tells us the slope, i.e. whether we're increasing or decreasing, whether it's positive or negative. And then we have f double prime, which tells us the concavity, okay? Concavity meaning it's some kind of description of the curvature. Does it look like a U or does it look like an N shape, okay? That's basically what the second derivative is. So second derivative tells us how the first derivative is changing. First derivative tells us how the function itself is changing. Second derivative tells us how the original function is curving. Okay, so we sort of have this hierarchy of derivatives. By the way, what would the units be? Well, the units of the function itself, okay, let's say that they are, I don't know, meters, okay, and then maybe the units of x are seconds or something like that. Then the units of the derivative are going to be the units of f divided by the units of the input, right? So meters per second. Or if we want to take it one level further, okay, we just again divide by seconds to get meters per second squared. So what does this tell us? This tells us that, look, the derivative of a distance function is a velocity function. It's measured in meters per second. The derivative of the velocity function, or if you want, the second derivative of the distance function, is measured in meters per second squared, which is a notion of acceleration, right? Acceleration. Okay, so this is about the second derivative. Loosely speaking, we learned already that, look, when it's curving down is when we have concave down. Concave down means second derivative negative. Okay, concave up, like what we can see from C to E, okay, means second derivative is positive. Okay? Any questions about concavity before we move on to something new? All right, doesn't seem like there are. So the only other thing, okay, well, we did learn this table will probably be useful, okay, for when you have those problems on the homework that are asking you about drawing functions or looking at functions and identifying where is the second derivative positive or first derivative positive. Okay, this table gives you kind of all the different shapes that you can have. You're either going up or you're going down, and you're either bending down or you are bending up. It's just one of those two things, okay? Or one of those four things, I guess. All right, so that's the table, and then the final thing we learned was how to do it with a table. Okay, so how to find out whether it's concave or convex, concave down or concave up. You can tell from a table based on whether the rate of change is increasing or decreasing, right? Second derivative positive means first derivative increasing, right? So this is what we check. All right. So what we're going to talk about today is something new, okay? I don't want to overwhelm you. I wrote too much text, but we're going to go through this slowly, okay? We're going to go through this slowly. So we're going to return our attention in section 2.5 to economics. Well, it's almost sort of bold to call it economics, really, but we're going to talk about cost, revenue, and profit is what we're going to talk about. So what did we talk about previously? Well, we had cost functions, we had revenue functions, and we had profit functions, which were, of course, the profit function was given by taking the revenue function and subtracting the costs. Right? But before, we said that they were all going to be linear functions like mq plus b, right? mq plus b. So these were linear functions before. And what we said the marginal cost is, or the marginal revenue, or the marginal profit, okay, was just said to be whatever is the slope of the cost function, or the slope of the revenue function, or the slope of the profit function, okay? So if the profit function is like pi of q equals, I don't know, 50q minus 600, okay, then the marginal profit is 50, just the slope of the profit function, okay? But now what we're going to do is we're going to consider the possibility that our cost function, our revenue function, and our profit function, okay, may not be lines. Okay, they might not be lines, but we still want to have a notion of marginal profit, marginal revenue, marginal cost. And let me give you a quick example of why this might make sense, right? If we have a cost function, a very typical way that your cost function might look is something like the following. Well, of course, you start at 0 because if you don't buy anything, then you don't, or maybe you have a fixed cost, okay? Maybe you can have a fixed cost if you want. But what's going to happen to our costs as we make more and more stuff, okay? As we make more and more stuff, the cost goes up. But what would be common to see would be a curve which looks something like this. Okay, why would this make sense? Because initially, when you're buying small orders of supplies, it costs more, right? But then the more you buy, the cheaper it is because you get, like, say, a bulk discount, okay? A bulk discount. Whereas if you were just buying things and it was staying the price no matter how many you ordered, it would look more like this straight line, okay? But this sort of represents, well, maybe your costs are not increasing as fast when you're reaching really high levels of production because you have, economy of size and discounts on your supplies, okay, when you make large orders, something like that. So we want to understand how to still study cost, revenue, and profit functions when they could be possibly wiggly instead of just straight lines. So that's sort of the motivation for today's lesson, or for 2.5 anyways. So what do? Well, last time, or rather what we've been doing in the bulk of chapter 2 is having this generalized idea of slope, right? The generalized idea of slope by saying that, look, if I have a function which is curvy, I can still sort of describe how steep it is at a given point by finding the slope of the tangent line, i.e. by finding the derivative, okay? So this can tell us the slope of a curvy function. So now that we're going to allow our cost, revenue, and profit functions to be curvy, then our marginal cost, marginal revenue, and marginal profit are going to be given by the derivative of those functions, okay? So it's just going to be C prime of Q for the marginal cost. The marginal revenue is just the derivative of the revenue function. And the marginal profit is just the derivative of the profit function. Okay, just the derivative of the profit function. So what you're going to notice is now suddenly the marginal profit, marginal revenue, and marginal cost, they all depend on Q. That's because if you have a curvy cost function, okay, then the ways that your cost is changing at two different production levels might be quite different. Okay, it might be quite different in terms of the rate at which your costs are increasing or the rate at which your revenue is increasing. So it's going to depend on, well, how much am I already making now? Which is why we sort of approximate the marginal cost, the marginal revenue, and the marginal profit by the cost of producing the Q plus 1th item minus the cost of producing Q items. Okay? So cost of producing Q plus 1 items minus the cost of producing Q items, roughly speaking, says the cost, revenue, profit associated with producing the Q plus 1th item. So Q plus 1th item. So whatever Q is, could be 5, then C prime of 5, so C prime of 5 is approximately the cost to make the 6th item. Because what do? We take the cost of producing 6 items minus the cost of producing 5 items. Okay? Yes?
Wouldn't you then always get 1 as the answer?
Wouldn't you always get 1? No, you would get, if we're in a linear function, then we're actually going to get the slope, right? Because c of q plus 1, let me show you what I mean. So c of q plus 1 minus c of q would be m times q plus 1 plus b minus m times q plus b. The b cancels with the b, the mq cancels with the mq, and we're left with just m. So actually it's sort of the cost of producing one more item, which if it's a linear relationship, the cost of producing the next item never changes, right? But it's possible if our costs are coming down due to bulk discounts that it could be different if our cost function is curvy, okay? So this won't necessarily always be 1 because you have to plug into the function, right? Okay, does that answer your question? Yeah, Alex. You're talking about this? Yeah. Okay, I probably just wrote it very unclearly. Q plus 1, and this is a dash th. Q plus 1th item. So this is th here. Q plus 1th. So if q is 5, then this is 6th. Or if q is 9, then this is 10th. Okay, it's the cost of producing the next item. Okay. Any other questions? So the only other comment I want to make is on the units. Okay, the units for the marginal cost, marginal revenue, and marginal profit functions, which remember, these are functions now, they might change. Okay, the units are always going to be, well, the units of any derivative are just the units of the output of the original function, which is dollars, and we're going to divide that by the units of the input, which are, I don't know, units or goods, like goods or services. Okay, so if I'm like mowing lawns, then this would be measured in dollars per lawn, right? We're describing the rate at which I'm making money based on how many lawns I mow, right? Okay, so that's marginal revenue, marginal cost, marginal profit. It's just the derivative of the cost, revenue, profit functions. Okay, so I'm going to quickly run through an example, right? So what is this one asking us? It says Radio House finds their cost function can be modeled by the cost function c equals 125 to the power q plus 10. We're supposed to estimate their marginal cost for a production level of 20 radios. See, 125 to the power q, okay, plus 10, it's like an exponential function. So depending on how many items we are producing, right, q or maybe 2q, right, the rate at which my profit or costs are increasing could be changing, right, at different rates. So what do we want to do? We want to estimate c prime of 20 in this case is what we want to do, okay? Marginal cost for a production level of 20 radios. So we want c prime of 20 is equal to, well, it's not equal to, but will be approximately equal to what we get if we did average rate of change on a small interval, about 20. So I'm going to do c of, say, 20.01 minus c of 20, and then I'm going to divide that by 20.01 minus 20. So on the bottom, I just get 0.01, and let's see what I get on the top. So we need 125, all raised to the 20.01. Okay, it's too big of a number, but I can't write it down, but I can add 10, and then I can subtract from that 125 raised to the 20th power. Plus, no, sorry, minus 10. Have I written something wrong here? Why am I still getting such a huge number? $125 to the 20th. Okay, let's try it with Wolfram. It's possible my puny calculator isn't strong enough for this. 125 raised to the 20.01, and I want to subtract from that 125 raised to the 20th. Damn, it really is that big of a difference. Okay, I guess that makes sense because this number is too big. I feel like there must be we must be missing a decimal here. I think that's what it is. Let's try that. Okay, that's a lot more reasonable. Yeah, I think I was missing a decimal there. Sorry about that. So if we change this to 1.25 to the power q, which sounds a lot more realistic, then we get on the top whoa. Then we get on the top 0.19-ish. Okay, so we divide by 0.01. In other words, we multiply by 100, and we get 19. Okay, we get 19. And the units here are dollars per radio. And the interpretation, okay, the interpretation is as follows. Okay, when I am producing 20 radios, oh, thank you. So the interpretation is when I'm producing 20 radios, okay, my marginal cost is approximately $19 per radio. Another way of saying that is to say, look, the 21st radio will cost about $19 to produce, because we're talking about the cost to the radio house. Okay, cost to radio house. All right, so despite being off by a factor of 10 to the 40, that wasn't too bad. Okay, so any questions on this one? Yes.
Why do you use 20.01 instead of like 21 if it's U+1? Like when you're doing the C of like 20.01 minus C of 20?
Just because I'm trying to estimate what is C prime of 20. So I can understand how you would be led to believe that we should use this, right? Yeah, we should use this. Well, again, this is an approximation, okay, which is essentially what? If you wrote this in a sort of average rate of change kind of a way, you would divide by q plus 1 minus q, right? Which q plus 1 minus q is just 1. So there's sort of an unwritten denominator of 1 here, and in which this is sort of describing an average rate of change of this function from q to q plus 1. right? So that's one way that you could approximate it. The reason I used 20.01 here was just because typically on your homework, when they're asking you to do do an estimation of a derivative, they're asking you to use some very small interval about the point at where you're trying to estimate the derivative. But that's an excellent question. You could just go ahead and do c of q plus 1 minus c of q, as long as the problem is asking you to estimate. Okay, they didn't specify how accurate your estimation should be. But yeah. Does that answer your question?
Yeah.
Okay, good question. Are there any other questions on that one? All right, then let's see. I'm trying to think if I want to run a group work real quick. I think I would rather move on. Okay. How much time we got? Yeah, I would rather move on to chapter 3. I think these problems are okay, but nothing special. So, really, what I want you to take away from section 2.5 is just the following. Instead of saying that the marginal cost, marginal revenue, and marginal profit are just the slope of the linear cost, revenue, and profit functions, we're now allowing our cost, revenue, and profit functions to be potentially curvy-looking things, in which case our new notion of marginal cost, marginal revenue, marginal profit is this sort of generalized slope, i.e. the derivative, or instantaneous rate of change. Okay? Any final questions on marginal cost, marginal revenue, marginal profit before we move on to chapter 3? Okay, it doesn't seem like there are, so I think that you're all going to be very excited by chapter 3 because we're finally going to learn derivative rules. And if you've taken a calculus course before, you've probably been waiting for this moment because it's a real pain to estimate derivatives. Okay, so previously what were we doing? We were taking, let's take an example of f of x equals to x squared. If we wanted to know what is f prime of 2, what did we have to do? We had to approximate it by the average rate of change of f of x from 2 to, and then like do 2.1, 2.01, 2.001, and look for a pattern, okay? And look for a pattern. And we have to do this really sort of cumbersome process of finding the slope of these secant lines, right? Finding the slope of these secant lines, which go from like here to here, and then here to here, and so on and so forth, to try to estimate what is the slope of the actual tangent line. So that was a pain. And today, what we're going to learn is some ways in which you can actually get not just an approximation, okay, but the actual value of the derivative for a handful of functions. Okay, and the first one we're going to do is the derivative of a constant function. Okay, so if f of x is a constant, okay, f of x equals to c. So think about f of x equals to, I don't know, -2. Right? What does the graph of f of x equals to -2 look like? It's a horizontal line, right? It's a horizontal line. And remember, the derivative, okay, the derivative is telling us how is this function changing? Well, to be constant is to not change, right? So what do we think the derivative of a constant is going to be? Yeah, 0, right? Because the slope is 0 everywhere. Okay, so that's the easiest one to do ever. Okay, so for example, part A, if I know f of x equals 175, what's f prime of x going to be?
0.
Just 0. Okay, so that's the easiest one to do. All right, how about if we have a linear function? Well, if f of x is a linear function, like mx plus b, okay, then now our function looks like it could have a slope. Okay? But the thing about a line is that the slope is constant everywhere, right? So if f prime of x describes the slope of the function at a given x value, well, the slope is the same no matter where you are on the line. It's just whatever the slope of the line is, which is m. Okay? Just m. So what would I get if I tried to do... Okay. Yeah, what would I get if I tried to do the slope of f of x equals to 19x? What would I get? Yeah, just the slope, which is 19. Okay, easy peasy. All right, I'm going to give you the next two rules in a row. Okay, the derivative of a sum or difference says, look, if you want to do the derivative of f of x plus g of x, then that's the same as just the derivative of f of x plus the derivative of g of x. Okay? So we call this property linearity. So the derivative is linear in that it basically just distributes over sums, okay? It just distributes over sums. So the derivative of a sum is the sum of the derivatives, is what that says. And it's not hard to see, if that's true, why the following should be true. The derivative of any constant times a function is just that constant times the derivative of the function, okay? It's easy to see why this should be true given the sum and difference rule, because multiplication by c is the same thing as adding something to itself c times, right? Okay, multiplication is really just fancy addition. Okay, so in light of that, well, actually, we're going to need to use rules 1, 2, and 3 to do part C here, okay? The first rule we're going to use is the derivative of a sum or difference, right? We have a sum, so we're going to use the sum rule, which says, look, the derivative f prime is just going to be whatever is the derivative of this thing plus whatever is the derivative of this thing, which we can do using rules 1 and 2 respectively. So the derivative of a constant is just 0, and we add to that the derivative of a linear function, which is just the slope. So we get just 6. Any questions so far? All right, so somebody help me out with the, we're not going to do all of these, but we're going to do the hardest one. 25x plus pi. How do I get the derivative? Which rules do I need to use? Yep.
The first two.
Yeah, the first two rules, and then also the sum and difference rule, right? So we have a sum here. So I need to do first the derivative of 25x. That's easy. It's just the slope, which is 25. And what about this guy? What's the derivative of pi? Just 0, right? Okay, just because it's a letter here, don't forget that pi is just a number, okay? Just like the derivative of 175 is 0. The derivative of 3.1415926 da 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 is also 0. So it's just 25 here. Okay, so don't let letters trick you up, okay? E and pi, they're just numbers. All right, so now we're gonna go ahead and learn some more rules. We're gonna learn the power rule. What are the, okay, maybe that's it for today. We're gonna learn the power rule. So what does that say? The power rule says we can find the derivative of a function which looks like x to the n, where n is a real number and n is not equal to 0. Okay, so think x to the 8, okay, x to the 4.5, etc. Okay, x to a number. Then the derivative is found via the following process. You take the power and multiply it down in the front, so n, and then we multiply times x, and we're going to have a new power, and the new power is going to be 1 less than it was before. 1 less than it was before. Okay, so we take the old power, multiply it down, and reduce by 1. Okay, take the old power, multiply it down, and reduce by 1. Okay, so a good example of that is this part A here. What do we say? F prime of x is going to be, well, we take the power comes down front, so that becomes an 8. And we multiply that with x, but the power is going to change. It's going to be 1 less than it was before. Since it was 8 before, the new power will be 7. Okay, the new power will be 7. Any questions on that first example? Yep.
What exactly is the d over dx mean?
So d over dx, when we write this kind of notation, I'm glad you asked. These brackets plus, maybe I can highlight this. So this stuff here means do the derivative of, okay, whatever's inside the brackets. Okay, so it's kind of like a function in the sense that you're plugging something in. But what we're plugging in isn't a number, it's a function. We're plugging a function into this thing, which we actually call it an operator. Okay, so this is the derivative operator. It takes as an input a function, like x to the n, and it returns as an output the derivative of that function. Okay, so that's what this notation is referring to. So this d dx just means do the derivative of, okay? Good question. Any other questions so far? Okay, so let me show you really quickly like what this actually means. Okay, let me show you what this actually means. Okay, let's return to our f of x equals to x squared. Because now we can actually find out what f prime of x is, right? It's just 2 times x to the 1, which is just anything to the first power is itself, right? So what is this telling us? This is telling us, okay, what is the slope of this function at various different points. We can plug in whatever x value and get the slope. So let me show you what I mean. If I were to say f prime of 1, well, what would I get? I would put a 1 in for x in the f prime function, and that would give me 2. Which is to say that, look, when the x value is 1, we have a tangent line. The slope of that tangent line is 2. And if I were to do instead, f prime of 3, what would I do? I would do 2 times 3, which is 6. Which is to say, look, if you go out to 3, I want to move this up here. So the slope of this guy is m equals 2. If I were to go out to 3 and find, again, the tangent line, then its slope is 6. So the derivative function, okay, we have found a rule such that if our function is like a polynomial, okay, we can find its derivative using the power rule, and we can input any number that we want, and the derivative function's job is to give us back the slope of the tangent line. And it turns out that the slope of the tangent line for a given input to the function x squared is just whatever that x value is multiplied by 2. That tells us the slope of the tangent line at any point. Okay? So this is what the derivative function is all about. Okay? So we're learning a sort of a cheat code for being able to figure out the slope without having to do this average rate of change business. We just go straight to the tangent line, and immediately we get the slope of the tangent line via this formula. Okay? Via this formula. So these formulas come from somewhere, okay? There's a way that you can prove them, which we're not going to do in this class because we don't prove anything. What we just say is that, look, there it is, and it's true. And if you want to know why, we can talk about it in office hours. Okay, so that's the power rule. So let's do some more practice with the power rule. Can I use the power rule on 1 over x cubed? How can I use the power rule here? Should I just do 1 over 3x squared? Ryan? Yeah, we have to be a little bit careful about how the rule is written. Okay? We have not learned how to do the derivative of 1 over x to the n. We've learned how to do the derivative of x to the n. Okay? So we can only use this rule when we can put our function in the correct form. We could use this rule on 1 over x cubed if I were to rewrite it, okay, if I were to rewrite it as x to a certain power, which, what should the power be? Not 1/3. 1/3 for a cube root. For a denominator, it's -3, okay? And then now I can go ahead and use the power rule, which says, look, if it's written in the form x to the n, you take the power, and then x, and then the power should be 1 less than it was before. So the new power actually should be -4, okay? If you want to rewrite it, you could rewrite it as -3 over x to the 4. Okay? So we have to make sure that if we're going to apply the rule, that our function looks like the function does in the rule. Okay, it's very tempting to start this one off like how I started it off and just say, I'm going to use the power rule. But we first have to rewrite it so that we can apply the rule. Okay? All right, and we're going to do something similar for part C, right? We jumped ahead a little bit in the last problem. We said we're going to rewrite this, and we know that square roots can be rewritten as a 1/2 power. So if I wanted to do the derivative, I just take that 1/2 power right down, multiply by x, and what's 1 less than 1/2? Well, 0.5 minus 1 is just -0.5, i.e. 1/2 minus 1 is just -1/2. So we get -1/2 here, okay? So just take away 1 from the power and multiply by the original power. Okay? So let's talk about the most complicated one. We're going to go to H here. See this one. Okay, what do we do for this one? Well, by the sum and difference rule, I know that the derivative of all of this jazz is going to be just whatever's the derivative of this, plus whatever's the derivative of this, plus whatever is the derivative of this, plus whatever is the derivative of this. Right? Okay, that's all I'm going to do. So starting off with x to the 4, that's the easiest one, I think. It's going to be 4 times x cubed. Now how about this one? What's going to happen with 2x cubed? Yeah, I'm going to write this out in a very long way, okay, so that you can see what I'm doing here. I'm going to use the constant multiple rule to say that the derivative of 2x cubed is going to be 2 times whatever is the derivative of x cubed. Okay, so I'm using two rules here. The first is the constant multiple rule, which says that the constant is going to hang out, and we're just going to multiply the constant times whatever is the derivative of the sort of meat and potatoes part of this piece, okay, which is the x cubed. So we do the derivative of x cubed, then that becomes 2 times 3x squared, which 2 times 3x squared can be rewritten as 6x squared, okay? So this 3 formally just came down, and we just sort of left the 2 there to be multiplied by this 3, okay? So, and the power became 1 less, yes? Okay, and then the next one, what kind of function is 5x?
Where are you getting the x squared from? You're taking 3 down.
So the 3 comes down due to the power rule, and then the power should be 1 less than it was before, so 1 less than 3 is 2. Okay, so it's coming from, here, let me write it all the way out. So d dx of 2 times x cubed is, by the constant multiple rule, I can take the 2 out and just do the derivative of x cubed. And I'm going to do 2 times, and now I'm going to use the power rule. The power rule says take this power down and then make it 1 less. So that would be 3x squared. And then if I multiply 2 with 3, then I get 6. And the x squared is still here. Okay, so the power rule says you multiply by the old power, and you make the new power 1 less than it was before. So since we started at 3, 1 less than that is 2. Does that answer your question? All right. Any other questions on that part? Okay, then 5x. What kind of function is 5x? Is it a quadratic? No, it's a linear. And the derivative of any linear function is just the slope. Okay? It's just the slope. So in this case, it's 5. And how about the last part? Derivative of 4? Just 0. Okay, so if you don't have to write the plus 0 at the end, okay? All right, so what happened? Our quartic term became a cubic, our cubic term became a quadratic, our linear term became a constant, and our constant term became 0. Yeah? Why 0? Because a constant function so if you have f of x equals to c, so some constant, then f prime of x tells you how is this function changing, right? Like, i.e., how is it going up or down, and how steeply? Well, it's not going up, and it's not going down. It's going straight across, which is to say that as you move from left to right, it's not changing at all. So the rate at which it's changing is 0 because it's not changing. Does that answer your question? Okay, how do we feel about these rules so far? We've got 5 rules in quick succession, which tell us basically how to do the derivatives of anything up to a polynomial, right? And some power functions, right? We can do fractional roots, right? fractional powers or negative powers. Okay, so it's a bit wider of a class than just polynomials. It's basically things like x to the power n and sums of x to the power n, right? Those are what we can do derivatives of now. Yeah? Any questions so far? I like the questions we've had up to now. Okay, then we're going to finish off with a group exercise, which is problem 3. So, we've all got the tangent line formula memorized, right? Okay, maybe not. I'm going to give it to you this time, but then we're going to work together on doing the tangent line approximation, okay? So t of x is equal to f of a plus f prime of a times x minus a. And this is the equation of the tangent line to f of x at x equals to a. So we're going to work on finding this tangent line. Okay, we're going to work on finding this tangent line, and then we're going to try to approximate f of 1.1. All right, so get in your groups. I'll be floating around to help. And Jacob also will be floating around to help. So just raise your hand if you want a little bit of attention from either of us. We have Wyatt here today. No Wyatt. Liam.
One power plus 2.5. Plug it in there and solve that. Does that equal a? Or is that equal to the x of the part and y?
I think that's equal to like f of y.
Doing all right, man?
Okay. Just trying to figure out what f of a is.
Why uses rules?
No. I think we did. Yeah. This is part of the process. I don't understand which terms you get something. It's because I keep going down and back. I don't know where I'm going to go after I get this shit going. So I don't know what I can do with it. I have no idea what I can go from there. Maybe we
Plus
just.
1a.
Yeah, that's what I'm thinking. I think we plug one in anyways, because there's an f out being a derivative up there, so we keep the non-derivatives like a solution. And then we get the derivatives of all of those, and then plug into one. And then that's our f.
Yeah, no. What we're going to do is one star and then we're going to put something that one oh yeah, all we have to do now is
2. So let's go to f of a equals 2. And then right there. Oh, we have to do those. So it's 2. That's 2. Plus.
yeah, so the first thing I have to do is find out what is that prime of x.
Minus 5. 4x.
And then from there, I can plug in one.
Minus 5. Plug 1.
Well, first we find the original, right? Plug in once. And that will tell us what it is. Yeah, pretty much. And then we'll add it right here. And we'll plug in the regular one, regular. Find out what this means.
One is so your A is the equation is
Give it a actual tension.
so
Plug in one.
This is just plug one in for the original, that's my FFA, and then the FFA is derivative. It's just what I got the derivatives to plug in. And then I just plug those terms in. That's
So
it.
I feel like that's valid.
That's it, I can think of. And that equals something.
And my observation like 5 minus 5 times. I'm not sure if that's right.
yeah. Your X is your is gonna be the 1.1.
Like,
So it's just 1.1.
Yeah. So 5 will be plug in one.
So it's
Yeah,
5.
because the X is gonna be whatever you're trying to approximate.
Yeah, so.
I don't. I'll plug all these numbers in, bro. No, actually.
Right. So you wrote this basically like if you take this y, that's f. So if you were to take y and
So your X is gonna be 1. So basically you're just gonna plug up to 1.
see how big that's exactly so that's f of a.
So and then your X minus I, your A is the 1.1. So it's just 1.1 minus.
Exactly.
So no, you're
There's
sorry.
a big road road and then that's your
The one
green
was
was
the
the
A.
A.
Your version.
The f of a is on the other side.
The F of A is what we just did.
That's right.
You're taking the derivative.
And what's your question? That looks correct for getting f prime of 1, right? But now we need to do the equation tangent. Right? So what we're gonna do here, right, is our A is 1, right? Our A is 1, so we wanna come up with this formula. T of x is f of 1 plus f prime of 1 times x minus 1. And we're taking A to be 1. Correct. X is 0 because
I don't know why
right?
this.
Depending on what the
Like,
X
how did I
value
manage
is,
to draw
try to
my
think
fingers
of
with my
different
hand?
thing, right?
I forgot about this. I
Actually,
deleted the app so long
X
ago
is gonna be
because
1.1. That's
it's so
Exactly. So you found out what this
I literally use it like
It's a little
once
confusing because it says X
every
F of 1, we can figure out
That's how I was. I used it like once a week.
Yeah, the X is gonna be 1.1.
And then
I was
once we
using
have
it a lot
those
before, and then
numbers,
Over the summer it was fun because like I was doing stuff and when I got here
no, it was
nobody
really
cares
fun.
about my like
Yeah, half of them are my studies, but normally I would just like cheat and save for when I was
oh I did that every day.
yeah, exactly. Yeah, exactly. Yeah, got it. Would anyone like a little more time to work still? Okay, some people want more time, so we're gonna wait. Oh, that's okay.
I basically just like post whenever I want to see what the hell my friends back home are doing. Like
That was
honestly,
like I just like doing it for
Right,
that.
we're doing this tangent line
Like-
and
like
x
X
equals 1. That tells you
what is
So
good?
what we're trying to do is we're trying to find
This is what happens at my high school.
No, I miss my hometown friend.
I know all of my little little seniors. I'm gonna get back in time to watch it again. More than that, honestly. Because like we start school in like mid-September and like end in like fucking June. So like they'll be graduating in like July. That's like normally how it is. So like I'll be there. I'll be there to go to the school and then like go see people. That'll be cool. I gotta like finish my finals and then like drive back immediately after because I have tickets to watch the PGA Championship
Oh, that's right.
in Rochester, which is it's at a course that I've played tournaments at before. So like, I get to go there. Damn, that pro played worse than me.
No, I think I'm supposed to go to like my friends and I are gonna go. So our prom is that Friday. So my friends and I are gonna go to our friends.
Yeah.
But if I don't make it, I don't know.
No, I know. And then like all my friends here are trying to like plan like a meetup, like the Outer Banks or some shit over the side. They're gonna get like a late house or some shit. I don't even know what's going on. But like, I don't.
My front people okay?
Yes.
Mentally or like.
I meant with respect to the example.
No comment.
All right, should we talk this one over? Okay, we'll talk it over real quick and then end for today. Okay, so we want to find the equation of the tangent line to whatever the hell this function is, okay? We don't know what the function is, we don't even know what it looks like, but we can find the equation of the tangent line using the formula. So the first thing to recognize is when you read these tangent line problems, they almost always tell you what is the point at which you are doing the tangent line at. This tells you that, okay, this corresponds with the part here, right? Equation of the tangent line to f of x at x equals to a. Okay, this time we're doing at x equals to 1, which means that a is 1. So the tangent line function is going to be given by f of 1 plus f prime of 1 times x minus 1. And remember, we're not going to put in 1 for x because ultimately we want a function which is a line, right? Once we plug in all of these numbers, okay, this is a number, this is a number, this is a number. When we multiply all that out, we get something like mx plus b, okay? We get something like mx plus b, the equation of a line. So our goal is to find out now what are these two numbers, okay? What are these two numbers? Well, the first one is easy to find. F of 1 is just 1 plus 2 minus 5 plus 7. Okay, so 3 minus 5, negative 2 plus 7, I think it's 5. Right? So I can rewrite this as 5 plus. Now how about f prime of 1? Well, I don't know what f prime of 1 is, but I can figure out using my rules what f prime of x is, and then I can plug in 1. So that's what I'm going to do. So f prime of x is given by the power rule. X cubed becomes 3x squared. 2x squared becomes 4x. Negative 5x becomes minus 5, and the 0 part, the 7 part becomes 0, right? Plus 0, which I'm not going to write. So now that I know what f prime of x is, okay, to find out what f prime of 1 is, it's as simple as plugging in 1. So f prime of 1 is equal to 3 plus 4 minus 5, which is 2. Okay, so the tangent line function is 5 plus 2 times x minus 1. Okay? Or if you wanted to, you could write it, you could simplify this further. It's 2x, and then minus 2 plus 5 makes a plus 3. 2x plus 3. That's the equation of the tangent line to this function at this point. Okay, and so now we want to use it to approximate f of 1.1. Well, that's the whole point of the tangent line, okay, is we have something which is weird and curvy. We know this thing goes through 1, 5. Something that looks like this, right? And we know that our tangent line looks something like this, right? And the idea is that, look, the output of the tangent function is kind of similar to the output of the actual function nearby 1. So if we just plug in 1.1, then we can get an approximation by doing 2 times 1.1 plus 3, which is 2.2 plus 3, which is 5.2. Okay? So that kind of makes sense. We expect that the height of the point just 0.1 away is probably not that different from 5, which is the height at 1, right? Okay, give me 1 second and I'll show you exactly what's going on here. Can someone read off the function for me? What is it? X cubed
Plus 2x squared
plus 2x squared
minus 5x plus 7.
minus 5x plus 7. So here's our function. And now let's draw the tangent line, which was 2x plus 3, right? Boom. We can see we found the equation of the tangent line. All right, we'll close there for today.